Hello everybody. In this lesson I will discuss tangent theorems and some easy examples. Introduction. A secant intersects a circle in 2 points. AB is a secant. A tangent intersects a circle in 1 point called the point of contact. PAT is a tangent. A is the point of contact of the tangent. The line from the center of a circle to a tangent at the point of contact is perpendicular to the tangent. And then your abbreviation there is tan perp radius, like that. The converse for this theorem is if a line drawn to a point on the circumference of a circle is perpendicular to a radius, that line is a tangent, and it's called the converse of the tan perp radius theorem. And you will use this converse if you have to prove that a line is a tangent. Another theorem is if two tangents are drawn to a circle from a common point, then the distance between this point and the points of contact will be equal. And then the abbreviation tans from same point. And there you can see that its AT's length is the same as BT's length. And you will use this theorem in analytical geometry. And now it's the theorem you've all been waiting for. The angle between a chord and a tangent at the point of contact is equal to the angle in the alternate segment. And we call this one the tan chord theorem. So when you go to the sketch, it means that the angle between the tangent and the chord is equal to the angle in the opposite or alternate segment. Or you can look at it the other way around. You can say the angle between the tangent and the chord is equal to the angle in the opposite or alternate segment, the tan chord theorem. And remember, you must know the formal proof of this theorem. You find that in lesson 23. And now your cheat sheet is complete. Here you can see this is tangent perpendicular radius. The next one, tangents from same point are equal, and then the tan chord theorem. The angle between the tangent and the chord is equal to the angle in the opposite segment. Now let's start with the converse of the tan chord theorem. It says if a line through the end point of a circle makes an angle with the chord equal in size to the angle in the alternate segment, then that line is tangent to the circle. And the abbreviation is, it's the converse of the tan chord theorem. And we're going to use this theorem to prove that a line is in fact a tangent. Now let's start with a couple of easy examples first. So the question is the same for all the sums. Find the size of the variables in each circle with midpoint O, where applicable. BA and AC are tangents to some of the circles. Give reasons for all statements. All right, we can start here on the first one and say that angle N is equal to angle P is equal to 38. And your reason is it's the tan chord theorem, because the angle between the tangent and the chord is equal to the angle in the opposite segment, or also P, the angle between the tan and the chord is equal to the angle in the opposite segment. And then angle M will be 52 degrees. And your reason is tangent perpendicular radius. So it forms a 90-degree angle there, so you subtract 38. Now in the next sum, what is happening there is I'm going to show you this first. This 80-degree angle over there, the angle between the tangent and the chord is equal to the angle in the opposite segment. So that angle over there will be 80 degrees. That one isn't labeled. So we can say that angle A is 80. Now first we used the tan chord theorem, and then the actual reason is since these two are equal, we have angles opposite equal sides. And then we can also work out B. B will be 20 degrees, and your reason, angles of a triangle. Angle Z is equal to 26 degrees, and your reason is it's the tan chord theorem. The angle between the tangent and the chord is equal to the angle in the opposite segment. Then angle X is also 26 degrees, and your reason is equal chords subtend equal angles. And then since this angle X is 26, we can say that angle Y will also be 26. It's the tan chord theorem. The angle between the tangent and the chord is equal to the angle in the opposite segment. Then on the next sum, we find M is equal to 30 degrees. There's M, and your reason is the tan chord theorem. K will also be 30 degrees, and that is angles in same segment. So K is 30, and it's that other 30-degree angle. That's the angle in the same segment. And angle L will be 90 degrees, and your reason is its angle in semicircle, since that line there at O is a diameter. In the next sum, we find that angle C1 is 90 degrees, and your reason is it's the tan perpendicular radius. Then angle N will be 30 degrees and is angles opposite equal sides. Can you see it was given that these two sides are equal since they are radii? So angle N will be 30. Then angle P is 60 degrees, and your reason is, can you see that it's angles of a triangle? And then angle O1 is 60 degrees, and your reason is the exterior angle of a triangle is equal to the sum of the opposite interior angles, which leaves me with Q. Q is then 30 degrees, and your reason is angles of a triangle. In the next lesson, I will deal with more difficult examples or riders on tangents. Click on the video in the left-hand corner to take you straight to the next lesson.